I'm Alberto Campos from Cablelabs, and this is material that I have prepared jointly with my colleague Senshen Jia. And we're going to be talking about the evolution of cable optical access networks. Just a couple of words about Cablelabs. We are a not-for-profit organization funded by cable operators around the world. We have 65 Cablelabs members worldwide, and our members have about 400 million broadband subscribers. But Cablelabs' impact goes not just to our members, but to the entire cable industry. In Europe, in particular, since we're at ECOC, we have 18 members that have about 90 million subscribers. More than half of our members are also mobile service providers. And in Europe, all of our members are also mobile service providers. This is one reason why mobile plays such a significant role for us. Let's just take a look at cable's network. In cable, our backbone, regional, and metro networks are probably not that much different in architecture than those from telco and mobile worlds. But where we start seeing differences in the access portion of the network. So we have these multiple hubs equivalent to central office that you see in telco world, maybe covering a little bit more area. But from these hubs, you have multiple bundles of fiber going into multiple directions. And from these bundles of fiber, as it traverses different areas, you peel off 6 to 8 fibers. That's the original design towards a fiber node. So you have dedicated fiber connectivity from the hub location to the fiber node location. The fiber node is where you have this transition from the optical domain to the RF domain. And from that fiber node on, you have this RF distribution over our coaxial network. The spectrum that we have today in coax allows us to have capacities of up to 10 gigabits per second. So let's take a closer look at the fiber node, which is that square depicted in the previous slide. So you have the fiber node here in the middle, and you have fiber connectivity to the hub. On average, most of our links from hub to fiber node are less than 40 kilometers. In Europe, that distances are much shorter. And from this fiber node, we have coaxial connectivity going into multiple directions. And you see these amplifiers and RF couplers that we call them taps, from where energy is tapped onto the households to provide broadband services. But this fiber node serving area is going through significant transformation these days. There are two flavors of evolution that the cable industry is embracing. One is called N+2 or node +2, meaning that out of a fiber node, you have at most two amplifiers that you traverse before reaching a subscriber. So this is a way of segmenting this fiber node serving area into smaller segments. So you dedicate more capacity to fewer number of users, thereby increasing the capacity per user. Another flavor that some operators are deploying is called the N+0 architecture or node +0, where you have fiber that has been extended to a deeper portion in the network, where you just have this fiber node, but then there is no amplifier in between the fiber node and the subscriber. So this is just a passive coaxial network from the fiber node to the subscriber. So you're segmenting even more. At this point, you are 250 meters, 300 meters away from the subscriber. So you are now approaching fiber ubiquity. So, and as you can see here, it's not just to distribute connectivity to the residential subscribers, but also to for backhaul connectivity, as well as for enterprise connectivity. So these are important portions of cable business. Just to give a couple of words about when we choose a new technology, when we want to introduce a new technology, we like to look at what is the total cost of ownership. So it's not just the CapEx, but also the OpEx, number of ports, powering considerations, cooling, space, etc. And in this day and age, where you have this exponential growth in capacity, you have to make sure that the technology that you introduce is going to last for a good amount of time, because you don't want to have frequent upgrades and when introducing new technology. You want to make sure that from a facilities perspective, that the reach of the technology is such that you're not going to be prompted to put more facilities, deploy more facilities in between to make up for any reach limitation. So we want to make sure that we use the fiber capacity as efficiently as we can. So wavelength spectrum is at a premium. That's our currency. And we want to have all the tools to take advantage of that. In cable, we have different type of signals. Some of the signals consume a lot of power. Our analog signals use a lot of optical power. We have to be also cognizant that what is the power budget as you put many optical signals within the fiber strand. But at the end of the day, we have to make sure that we efficiently leverage our existing fiber infrastructure, and we design based on that. So we are bullish on coherent optics as a technology that will help us evolve our optical access networks. And while traditional coherent optics provides high capacity in implementations that you have coherent optics in backbone and regional networks, it also still at a high cost to be deployed in the access portion. But with access optimization, we are looking to increase the higher capacity of coherent optics technology, as well as simplification that will allow us to achieve lower costs. So ideally, we would like to leverage these features to drastically reduce the cost per bit of these optical access networks. So some examples of how to achieve that. In access, we're talking about shorter links. Most of our links are less than 80 kilometers. A lot are less than 30 kilometers. We're not talking about thousands of kilometers like you would have in backbone, or hundreds of kilometers like you would have in regional networks. So for these distances, we're talking about the amount of dispersion is much lower. You don't have cascading amplification, so distortion and noise are also lower. And that is going to allow us for a generous link margin, and we can leverage this link margin to relax optical component requirements. At the same time, this new environment that is much shorter in distance requires much less chromatic dispersion compensation. You see in this chart how in the axis there is almost negligible DSP processing for chromatic dispersion compensation, and all other functions are also greater simplified. So this is going to result in reducing the footprint of the ASIC, but at the same time, because of the link margin, improving the efficiency of our optical transmission. I mentioned before that in the access, in many occasions, we don't have amplification, inline amplification in between because of the shorter distances. So we can operate in other modes, such as full duplex transmission that I'll describe next. In full duplex coherent optics transmission, and this is prompted because in cable, sometimes we need to reach many endpoints where we have just a single fiber available, a single fiber strand available. So when you have a single fiber strand available, you can transmit using circulators in front of the transceivers in both directions. So bidirectional transmission using same wavelength on the same fiber and using a single laser, which at the end doubles fiber capacity, and capacity is one of the things that we wanted to improve. Just to see the performance here, the solid square curve is single direction, and the hollow curve is the corresponding full duplex curve, and there is less than 1 dB power penalty for adding this full duplex reverse direction. There are other opportunities to simplify transmitter. I mentioned the relaxation in the link budget. We have a generous link budget, and we can use that to relax optical components. We have demonstrated QPSK and 16 QAM transmission at 32 gigabaud using 1 megahertz line with DFB lasers. So you can also lower the cost like that. Quantum dot lasers are attractive because they provide narrow line with our simple structure. So this can also be introduced in the access. Simplification of the IQ modulator is also another alternative. And we have, by cascading intensity modulator with a phase modulator, using synchronization and pre-equalization, we can reach all the constellation points in an IQ constellation, avoiding the complexity of these nested IQ modulators that are used in traditional coherent transmission. Then there is another technology that we think that we can apply in the access, which is leveraging optical injection locking that I'll describe next. If you have an FP laser, you're transmitting many modes, right? This is a very basic laser, so you transmit many modes, and you cannot distinguish phase using that type of laser. But if you injection lock this laser using a high quality parent laser like an ECL, then this ECL is exciting this FP laser, and this FP laser now is lasing with a much higher spectral purity so that you can generate this signal and is useful for coherent transport. The signal that comes out of an parent laser can be shared by 64 child lasers. And by sharing this expensive laser, you lower the cost. And this is actually very suitable for the type of topologies that we have in cable, where you have the hub location from which you have many fibers going into multiple directions. So we're taking advantage of topology for this type of technology. One of the metrics here are shown here how they perform. The black curve is the ECL performance, while the red curve is the injection lock performance. So almost no difference in 32 gigabaud QPSK, no difference in 16 QAM in the middle. You start seeing the difference in 64 QAM, but it's still correctable with FEC. So you see here the FP prior to injection locking. As we introduce injection locking, now you have the high spectral purity signal. So the line width is exactly the same as the ECL. So because we want to leverage as much our existing fiber resources, we want to fully load this with optical carriers, and we need tools to manage the wavelengths. So traditional ROADMs that are mostly for long-haul and regional networks are really too complex and too expensive and have too much functionality that's not needed in the access. In the access at most, we have fiber rings. So 2-degree ROADM functionality is enough. And since we have only fewer add-drop ports, it results in a lower loss device. So optimization and design towards this type of use case results in a much simpler device. And if you use integrated components like ring resonator-based devices, it becomes now a promising tool for introducing this functionality of wavelength manipulation at the edge. So to explore further, as we replace all these maybe lower efficiency signals like analog optics or IMDD that we have in cable with coherent optics, in essence, you are reclaiming your spectrum. You're making more optical spectrum available, so you can use it for other purposes. In the access, because we are dealing with much shorter distances that are non-amplified scenarios, we can introduce L-band and not wait until amplification in L-band becomes popular. We have that in coherent optics, the costs are coming down, and we see that in the future they're also going to play a big role in PON technology. We can take advantage of the superior performance of coherent-based technologies to have a much greater performing PON systems. And another technology that is may play a significant role in the access are optical frequency combs, because we are looking to efficiently fill up the optical fibers with optical carriers, and having an optical frequency comb is enabling this. And all this introduction of technologies really prompts us to next generation management. So just to recap, we have reviewed the cable access environment, in which we're dealing with the special characteristics of shorter lengths and simpler environment that allow us to optimize for this type of scenarios. We have reviewed a bunch of technologies, but at the end, this is about maximizing the resources that you already have. We already have in cable a lot of fiber that is very deep, that is close to the subscriber, and about evaluating the total cost of ownership, not just the endpoints. Thank you very much. And back to you, Glenn.
Well, thank you very much, Alberto. I appreciate the readout. We had a couple of questions. One of them came from industry veteran Stephen Hardy, and that was, what was the timing, or there was two facets of it, but first was the timing of the coherent optics, or the specs and requirements that you guys, and you explained it well, but you didn't really mention any timing in there. What might be the time frame that we could expect any either field trials and or deployment of that?
So, Cablelabs develop specifications for 100 gig and 200 gig point-to-point coherent optics. Those specifications are out and are public. We have had interops where we have trial out these specifications, the 100 gig specifications. So elements for point-to-point are out that could be used for backhaul. So initially we see that coherent optics use initially for backhaul of multiple fiber nodes or multiple enterprise connectivity links or backhaul connectivity from mobile aggregation. So initially it would be an aggregation tool, but as costs come down, then you can use it for direct connectivity. So there is one element that is still missing in our tools to start deploying this technology, which is the device that translates the coherent optics, that terminates the coherent optics link, and that connects to the multiple points that you want to aggregate. We call this a coherent termination device. We have been talking to different vendors. Some vendors have prototypes of these. So I would say that when we see prototypes, we will be ready to start deploying this aggregation use case.
Thank you very much. I appreciate the second half of his question was, are there any other technologies that might be used instead of the N+0 node? Because that's pretty disruptive or anything. So, are there other things that are being explored in that context?
So this varies operator by operator. They have different decisions how far they want to deploy. They want to put fiber deeper, but they vary this. So it's all the way from just gradually based on demand splitting the nodes to these step function type evolution steps that go to N+0 or N+2. We have Canadian operator members that are predominantly N+1, so there are all these ranges, but I mentioned just the two more popular ones that the industry has been looking to evolve to.
Yep, fair enough. Like you said, it's there's lots of different networks. As you say, you have networks across the globe and many different operators, and each one's going to be unique in some way or another.
And just to that effect, because our industry is not just residential traffic, right? It's demand from cellular, demand for enterprise, and many times the fiber deployments are pushed by other reasons than residential. So you might just piggyback one driver from another and take advantage of this fiber deeper deployment.
Yep, exactly. If you're going to dig up a street or fill a conduit, there's no reason not to put in more fiber when you're doing it, right? Thank you.